It is kind of staticky, isn't it? Every time I turn. Okay. For our first example, you don't need to write down everything, just write down the highlighted points. So, properties of logarithms, your essential question is, where in the real world are logarithms useful? How do properties of logs compare and contrast to properties of exponentials? I probably should have put the word exponents. Exponents. Because exponential functions is something different. Exponents. There we go. Oh, forgot the T. Exponents. Is that good? Okay. So, for this example, would you please write down anything that sounds important? You don't have to write it down word for word. Just highlight the important information. In December 2004, an earthquake hit with magnitude 9.3 on the Richter scale. Jaden, you can go to the attendance office. Okay, 9.3 on the Richter scale, off the northwest coast of Sumatra. Where's Sumatra? Apparently right next to Indonesia, and Malaysia, and Thailand. Alright? Where are you from? Thailand. So when did you move here? Okay, so like 5-6 years ago. Do you remember Thailand at all? Kind of. So, but this is where she's from, guys. It's a little island, right? Next to Malaysia. Anyone else from Thailand? Yep.
I think my grandma.
Okay. Sumatra is right next to Indonesia, a little across the canal-ish Bay Area from Thailand. All right. So, 2004, 9.3 magnitude earthquake hit Sumatra. The diagram shows the magnitude of an earthquake that hit Sumatra in March 2005. So we got 2 earthquakes within what span of time? Oh, it's quicker than a year. Months. December to March. December they get one, a few months later, get another one. The formula, log, these are i's, capital I's, okay? Log I1 over I2 equals M1 minus M2 compares the intensity levels of earthquakes, where I, capital I, is the intensity level determined by a seismograph, and M is the magnitude on a Richter scale. How many times more intense was the December earthquake than the March earthquake? So you should have been writing highlights of that, summarizing it, just the important information. Arbor, what was something important?
I wrote down 9.
And also a little more detail, what did the 9.3 magnitude come, when did it come? Yep, that was the December one in 2004. Is 9.3 magnitude kind of a weak earthquake? No, it's a huge earthquake. Who's been in an earthquake? Anyone? I have a few. Styles, where were you? Were you just raising your hand for fun? Or were you in an earthquake? It was so traumatic you can't talk about it? Okay, interesting. Was it Nathan? Did you raise your hand? Ooh, that's scary. And the bridge was probably like swaying everywhere. Whoa.
2002, like towards the end of the war in Bosnia.
Are you from Bosnia?
Yeah.
Oh, I didn't know that. Huh. And you're from Bosnia. Wow. I love Cottonwood. It's so great. We have all these cultures. It's so cool. I need to go travel the world more. Yeah? A big one? I was going to say, the only earthquake I've been in I slept through. But it was a Utah earthquake, so it was a little tremor in the middle of the night. And my mom woke up, and I'm a really deep sleeper, so I had no clue what was going on. But, wow, that's intense. We're due for an earthquake, like any day here in Utah. It's supposed to be a big Kahuna earthquake. Yeah, the Wasatch Fault line, right? I took a geology class in in college, and I'm just going off of my geology professor's word on this, but I mean, he has a PhD in geology, so I think it's true. He's told us in class that it is illegal in Utah to build a public building on a fault line. But someone yesterday said that they were in Manti Junior High when there was an earthquake, and it split down the boys' bathroom and like the floor apart or something. That'd be awkward to be in the bathroom at that time. But he said he wasn't in the bathroom at that time, but it went through the bathroom. So I thought that maybe it's because it's an old building. Maybe the law was made after. I don't know. But the Salt Palace is made on a fault line. He told us this in class. And in order to get around that law that you can't build a public building on a fault line, they brought all these geologists in and to say, well, it's not technically a fault line. It's something very similar to this. So, moral of the story, don't be in the Salt Palace when the big earthquake hits, because it's all going to come crumbling down. Yeah?
So if you're on a fault line from the groups, are you just going to like fall into like the middle of the...
I don't know. I think the plates just shift and you'll like
fall into it and just get...
Well, it depends where you are. If you're like straddling the fault line, you might. It depends how limber you are. If you're gonna be able to do. You're a cheerleader. You can probably do the splits and you'll be fine. Okay, moving on. Okay, that was our earthquake story time. Let's hope we're all safe when that big Utah earthquake happens. What else was important, Haley?
The fact that I is
I is the what? Yes, we have to know what these variables mean. I is the intensity level determined by the seismograph. Styles? Oh, guess what? There was information on the picture. Right here. 8.7 in March. Yeah, so we can gain information from the picture sometimes. Noah? Yes, we definitely need the formula. Anything else? Thank you. I can think of two more things we need to know. Yes, thank you. M is magnitude. What else do we need to know? The question. You always have to know what you're trying to answer. The question is, how many times more intense was the December earthquake than the March earthquake? Okay, you'll have a couple problems like this on your homework. We will have to use this formula, so make sure you have the formula written down. I'll write it larger right here. It is log capital I1 over capital I2, the ratio of the intensities, equals M1 minus M2. Okay, make sure you have that formula written down. So, we'll use the formula to figure out how many times more intense was the December earthquake than the March earthquake. You can tell it was a more intense earthquake because 2004, the magnitude was 9.3 versus a few months later in March, the magnitude was 8.7. So it was slightly smaller, but still, that's a pretty powerful earthquake. Okay, so let's fill in the formula. Log is log. Do we know intensity of the first earthquake? No, we don't, do we? We don't know intensity of the first earthquake. Do we know the intensity of the second earthquake for I2?
Yeah.
What's the intensity of the second earthquake then? That's the magnitude. So do we know the intensity? So we actually don't know the intensity of either one, right? Now we do magnitude 1 minus magnitude 2. Good. 9.3, December's magnitude, minus 8.7, March's magnitude. Okay, so we're going to use our log knowledge to solve. And we've done basically lots that we did this at the beginning of class when we were reviewing our homework from last time. We will need to solve this. So what do you think we would need to do first to solve for the intensities? You see anything there we can do? Yeah, we can do the subtraction. 9.3 minus 8.7. Heather, what would that simplify to? 9.3 minus 8.7. What's that difference? Yeah, but what is the answer?
Oh.
Okay, how far, I like to start at the smaller one and work my way up to a whole number. How many more decimals does 8.7 need to get up to a whole 9? Like, how many more tenths? It has 7 tenths. It needs, what? 3 more tenths, so 0.3. And this one's how many tenths over? This is for Heather, thank you. This one's 0.3 over 9, right? So this one needs 0.3. This one already has 0.3, so together it's 0.6 apart. That's how I do it in my head. I don't know if that helps anyone. But when I do multiplication or decimals, I try to get to the nearest like 10 or the nearest whole number. Does that help at all? Well, we're just trying to subtract, and that's the trick I use in my head, is I just get to the nearest whole number. 8.7, I know 0.7 needs 0.3 more to get to a whole number. And this one's 0.3 over the whole number. So 0.3 plus 0.3 is 0.6. Or you can think money, if that's easier for you. $9.30 minus $8.70. There would be 60 cents difference, right? So 0.6, okay? Okay, so that takes care of the right side. Log intensity 1 over intensity 2 equals 0.6. Okay, well, let's see. The base of the log is not written. So if the base isn't written, what is the base? Do you agree? The base is automatically 10, which is great because our calculator can do a 10. So can we just grab our calculators and go log base 10, I1 divided by I2, and it'll give us the answer? Yes or no? Can we just pull up the calculator? Let's try it. If you don't have a calculator, grab one. Okay, do you see the log button? Raise your hand when you find the log button. Okay, M, where's the log button?
Right next to the 7.
Right to the left of the 7. So we hit log. Now, the problem said I1 divided by I2, so where's I1 and I2? What? Like X divided by a different variable? I don't know how to do a different variable. This one. And then hit enter. Okay, let's look at the problem. Do we know I1 and I2? No, so we can't just plug it into the calculator right there. If we knew everything on the left side, we could plug it into the calculator because it is base 10. But we can't because we don't know I1 and I2, and because it's an unknown on the left side. So we can't just jump out of the calculator. So instead, we should follow the 5 steps that we did when we did the problem you guys asked for on your homework. How did we solve for the log? We changed to exponential. Thank you. We will use the calculators in just a minute, so you'll need those anyway. Change to exponential, starting with the base. So our base is 10. Okay, base is 10. Joseph, what do I raise 10 to? Circle of logs, or circling, right? So we're going to circle over to what number? The 0.6. Okay, so we have 10 to the 0.6 equals the ratio of intensities, I1 over I2. Okay, could our calculator do this one, 10 to the 0.6? Are these all numbers? And our calculator can do any exponent we want it to do. It has, limitations on logs. So now we can actually plug that in. So now that you have your calculators, let's type in 10 to the 0.6. 10, you have to use the caret button. Make sure you put a decimal. 0.6. Jaden, I'd like you to get me the answer, please. Round to the nearest hundredth. Okay, I gave you a calculator. Type it in, please. It's not hard. Type it in. 10. 10. Come on. Everyone else is doing it. You can do it too. Okay? Clear that stuff out. Now write in 10. To the, it's this button. Because we're in math class right now and we do our math work in math class. Right here is the exponent button. Hit that button, please. 0.6. 0.6. And hit enter. Okay, what are the first three numbers? 3.98. Good. After the 8, there's a 1, so should it stay 3.98? Yes. Hit enter, we see there's a 1, so we let it rest, 3.98. Okay, so we get 3.98. Thank you, Jaden, for doing that. So what? What is 3.98? The intensity or something. Can you be more specific? Read the question again. How much more intense? Which earthquake was? December's earthquake than March's, okay? So with story problems, you should explain what your answer means. December's earthquake was 3.98 times more intense than March's earthquake. That is your answer. South? That's a good question. I think on page, you have your book? Yeah, on page 333. There's a chart there that shows the Richter scale. And it does go up by, I don't think it's necessarily 10 times greater, but you can see what it multiplies by right there on the scale. All right. Great. What? Hurry. Sorry, now I've changed my page. I'm on the wrong page. All right. If you guys would open up your books, please, to page 334. Open up your books to page 334. We drew this picture briefly last time. Now we're going to draw on our notes so that we understand what are these logarithms representing. Open up your books, please, to page 334. We're going to show what a log is in relation to exponentials. Page 334. See that blue box at the bottom? Have a volunteer read the first paragraph of the blue box, nice and loud. Loud, booming voice. Okay, Noah, thank you.
A logarithmic function is the inverse of an exponential function.
Okay, wait, pause. Sorry, I'm interrupting. It's a, what's the key word there? Inverse. The logarithmic function is the inverse of the exponential. Okay, keep going.
The graph shows y equals 10x, y equals log x. Note that 0, 1, and 1% are on the graph of y equals 10, that 1 and 1 are on the graph of y equals log x.
Thank you. So, he read this for us. Y equals 10 to the x and y equals log x are, what's the key word? Inverses. They are inverses. So what does that mean? Okay, it shows you a visual on the book, and we're going to draw it out. Yes?
It means it's flipped.
They are reflected about something. Yeah. So let's go over that again. If you notice, the chart is just looking at the positives. So we're going to draw just the first quadrant up to positive 10. Okay, so we draw an x and y axis for the first quadrant to positive 10. And labeling means putting x and y. It also means putting numbers, so I know what you're counting by. Taking notes. Okay, we're first going to graph the y equals 10 to the x. So, our smallest x I have on this graph is 0. And then we work out to positive 10. Okay, so Austin, 10 to the 0 power, do you know what that is? So we can get a point on the graph? You can do the next one then. Does anyone know what 10 to the 0 power is? 1. Anything to the 0 power is 1. So if we plug in 0, we get 1. So that's the point on the graph. 0, comma 1, right here. 0, comma 1. If we move to the next x is positive 1. So back to Austin. Do you now know what 10 to the first power is? 10. Good. So that's the point. We plug in 1, we get 10. So it's a point 1, comma 10. 1, comma 10. And this is beginning our exponential. Once we plug in a 2, we're up in the hundreds, because 10 squared is 100. I don't want to graph that, so I'm just going to stop right here and draw my exponential curve for y equals 10 to the x. Maybe I'll delete this 5 because it's kind of in an awkward spot. Okay. Now I keep throwing this word inverse. Inverse, inverse, inverse. The log function is an inverse of this graph, where literally the x's and the y's are going to switch places. Okay, so right here, we have on our exponential the point 0, 1. We're going to rotate those around, switching the x and the y. Instead of 0, 1, it would now be what point? 1, 0. So on our log function, there's a point 1, 0, which is right here. That's the point 1, comma 0. Same with 1, comma 10. If we switch the x's and y's, what point do we get? 10, 1. So we go right 10, up 1. 10, 1. 10, comma 1. This is what the log function would look like. You take the x's and the y's and you really just switch their places. And what's happened is, you mentioned rotated or something like that. It's being reflected over this dotted line. The green is being reflected to where the purple is. So does anyone know the equation for this line that goes right through the middle of the first and third quadrants? Yeah? Can I say y equals x? Just reverse it. But yeah, y equals x. It has a slope of 1, 1x. Okay, so it's a reflection over that line. That's where we get the log. Okay, you don't have to graph those on this assignment, I don't think, but we are going to, you do need to know that though. Okay, next example. Describe how the parent function compares to the graph of, or describe how the graph compares to the parent function. Example 2. We've done this many, many times this year already, so this isn't too new. Describe how the graph compares to the parent function. Describe how the graph compares to the parent function. Okay, when it says describe how the graph compares to the parent function, it's just asking for transformations. Okay, we've talked about transformations before, so you guys, once you see this, you'll already know the answers. You should. Y equals log base 2 of x minus 3 plus 4. Log base 2 of x minus 3 plus 4. Raise your hand if you remember us talking about A, H, and K in class. A, H, and K. Raise your hand if you remember us talking about A, H, and K before in class. Okay. Only about half. I think we should have a few more than that. A, H, and K, no matter what the function is, absolute value, quadratic, square root, cubic, rational, and even logs. We have an A, an H, and a K. Are they always in the same location, A, H, and K? Yeah. So it tells us the exact same things. We've been studying these for a while, so we should know the answers to this already. A, H, and K tells us specific things about the graph. Benito, do you remember what the H represents? Horizontal. Good. Horizontal shift. And in our heads for horizontal shift, what do we think? Thank you. Opposite. So, ringing a bell, I hope. Okay. What about the K? What does K represent? South. Vertical shift. Okay. Aiden, what word do we say in our head for vertical shift? Same. Good. Opposite. Same. Okay, and the A is representing the change in the steepness of the graph. Okay, so what is our value of A on this example that's in green? What? 1. It's not there, so it would be a 1. Does timesing by 1 do anything? No, it doesn't. So to list the transformations, we should list 3 things. We should say what A does, what H does, and what K does. So this A is 1. So since A equals 1, there is no change in the steepness. If the absolute value of A was greater than 1, we know it's a vertical stretch. It gets steeper. If the absolute value of A is between 0 and 1, usually a fraction, okay, it's a vertical compression. We've talked about those before. All right, I would like you to turn to your neighbor, please, and describe what the minus 3 does. It requires 4 words. We've done this before, so you should know this. Describe what the minus 3 does to the graph. It requires 4 words to describe it. Turn to your neighbor and tell him, please. Okay, raise your hand if your neighbor knew what they were talking about. Okay, Chibs, what did your neighbor say? I need one more word. He said horizontal shift. What was the next word? Of the right? Right. Do we agree it's right? Because we think opposite. So if it says minus, we think right. Right 3. Okay? Turn to your neighbor, please, and tell them what the plus 4 does to the graph. Turn to your neighbor, please. 4 words to describe what plus 4 does. Okay. Emmanuel, what are the 4 words? What do we think? Is it good or not good? Good. Vertical shift up 4. Now, I just want to make you aware of another vocabulary word. We usually say shift here, but also you could call it translate. Translate means that you're not changing the shape, you're just sliding it over left and right or up and down. That's shifting. It's not changing the shape. We could also say it translates right 3 or it translates up 4. Okay? So just be aware, you could see this word called translate. Even though we say shift, You could also say shift. So both are common. Okay, we're going to take a quick stretch break before we go to properties of logs. So if you need to get a drink, you may go get a drink. Where's my pause? All right, break's over. Put cell phones away if you've pulled them out, please. All right, we're going to move on to properties of logs, which is another semi-abstract, but we've kind of already learned it. If that makes any sense at all. All right, example 3. We're going to start with properties of exponentials and logs. Properties of exponentials and logs. Now, through this year, you've probably heard me sing a little song that you probably think I'm crazy because I really can't rap. I will, Styles. I will. Okay. With our exponents, we've had rules you've learned for years now. What are those rules, Styles? Okay, it goes like this, Styles. No, I'm smiling, I can't do it. Okay. I'm not a real rapper, sorry. No, but you guys are making me laugh. Okay, because when dealing with these oh, she's giving me a beat. Okay. It is. Okay. Yeah, because when dealing with these exponents and the base is the same, we got some rules, we ain't no fools, and we ain't playing games. When we multiply exponents, we do what? I know, I'm a terrible rapper. I wish I was Will Smith. Okay. That's the only rap I can do is from Fresh Prince. Yeah? In West Philadelphia, born and raised in the playground, so I spend most of my days. Okay. Alright. Man, this is recorded. This is so embarrassing. Okay. A to the 5th times A to the 2nd. When dealing with these exponents and the base is the same, are their bases the same? It rhymes. They're just rhyming styles. That's all I'm doing. Just rhyming. Are their bases the same? Yes. Okay. When we multiply exponents, what do we do with them? Add. Because when we multiply exponents, we add. Multiply, add. Multiply, add. So this becomes 5 plus 2, which equals 5a. A to the 7th. There's a reason I'm talking about this right now. The same rules apply to logs. Okay? When we have 2 logs and the base is the same, we multiply. Multiply, add. Multiply, add. So, like log base 4, log base 4 of m times n would split into an addition problem. Log base 4 of m plus log base 4 of n, as in Nancy. This left side is called, these are the single logs, and I want to write a song called All the Single Logs, All the Single Logs. Wouldn't that be fun? All the single logs, all the single logs. And the right side will be our expanded form. And for your homework tonight, expanded, yeah, let's put expanded. You'll be taking a single log and expanding it, or taking an expanded log and compressing it into a single log. Okay, so you'll have to be used to going back and forth. This rule right here is the product property, because the answer to a multiplication problem is the product. Okay, so you have to remember multiply, add, or add, multiply. Those two go together. There's a connection with multiplication and add in exponents and logs. Okay. Next one. We said when we multiply exponents, we add, multiply, add. But when we divide, then we have to do what with the exponents? And when we divide, then we have to subtract. Now, we have to go in order. We have to subtract. 8 minus 3, top to bottom, which would become a to the 5th. This would be the quotient property of exponents. because the answer to a division problem is the quotient. Write your notes, please. Okay, and same thing will happen with logs. Division and subtraction go together. And when we divide, then we have to subtract. And when we subtract, we have to divide. Okay, so if we have log base 6, it has to have the same base of, say, b over c. It would expand into subtraction, but must go in order, top to bottom. What letter was in the numerator? What variable is in the numerator? B minus the denominator, log base 6 of c. Okay, so exponents have the same properties as logs. It's just a little more abstract than logs, but it's the same idea. When we multiply, we add, multiply, add. And when we divide, then we have to subtract. We have to subtract. We have to subtract. Good. That's the point. It should get in your head. Okay, we've also talked about this rule already today on exponents. What happens if we have m squared raised to, say, the 4th? What do we do when we have an exponent raised to another exponent? Multiply. Good. This is called the power property. The power property. And these two would be times so that we would get m to the 8th. Well, there's also a power property in logs. Okay? If we have, say, log base 7 of r squared, log base 7 of r squared, this exponent 2 needs to be multiplied. So what we do is we bring it in front and multiply it to the log. 2 times log base 7 of r. Okay, so it's still multiplication. It's slightly different though. We're going to pull it in front. Yeah?
Is that like the same thing with any power? So it's like m, like, keep going like 9, 9.
Yeah, you just multiply it forever. You're saying power, 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 power. Lots of powers? Okay, yeah, we're going to die before Styles finishes saying all of his 9s. Okay, so these are the rules of logs we're going to go over today, running a couple examples, and then, yeah, then we'll be able to work on our assignment. So I forgot what example number we're on. 3. Example 3, using the properties above. All right, there are 2 different directions you'll see. You'll either see what is each expression written as a single logarithm, so you want your answer to be a single log, or you will see what is each logarithm expanded. So that's why I titled this left side is all single logs, and this right side is expanded. Okay, so make sure you know which direction you're requested to do. So for us, first we're going to go to single logarithm. What is each expression written as a single log? Yeah, if you put example 3 on the properties, you can say this is example 4, because I think I did say that it was example 3. So either way. Okay, we have log base 4 of 5x plus log base 4 of 3x. We want to have this written as a single log. What's the operation currently between our logs? Addition. So when we do what? We have to add. When we what? We have to add.
Since we have the same 4, wouldn't it be log for 8x?
You're really close, except for you have to multiply them. So since these are add, we have to multiply. Multiply, add, multiply, add, multiply. Even warmer. You're getting there. Ariana, you're getting there. So we have to multiply. They have the same base, correct? You can only combine these when they have the same base. The base is 4 and 4. So we have log base 4 of, now these have to be times, 5x times 3x. So it would become 15x squared, right? X times x is x squared. Log base 4 of 15x squared. Okay, you still have a question? Yes. Is that high enough? Need further? What are you copying? It's good? Okay. Okay, so multiply and add go together. Also, if it starts with add, then you go to multiply, back and forth. Multiply, add, multiply, add. And when you add, you have to multiply, add, multiply. Make sure you have those. I hope that little rap, the lack of my skills rapping, is in your head, and you remember multiply and add go together. Yeah?
But have you seen that video where he's like 9, 9, 9, 9, 9, 9?
Oh, you were actually quoting a video?
Yeah.
I have not seen that video.
From like Bruno, that guy.
No idea what you're talking about.
He's like scientist, invents the world's biggest computer, and he's like, yeah, but can it go 9 times 9, 9, 9, 9, 9, 9, 9, 9?
All right, well, Styles, if we have time at the end of class, you can find that video for me, and I'll watch it. All right, can I scroll a little bit? All right, let's try another example. Again, changing to single log. Example 4. 2 log base 4 of 6 minus log base 4 of 9. 2 times log base 4 of 6 minus log base 4 of 9. Okay, same directions. We're going to write this as a single log. Yes? Correct. They have to be, that's what makes them a like term. They have to have the same base. Yes, they have to have the same base. Same with exponents, they have to have the same base. Okay, so if you look up here, where is it? I saw that we had subtraction. So when we do what, we have to subtract. What and subtraction go together? Divide, subtract, divide, subtract. Now, let's go in order. Subtraction and division. Make sure you're careful on the order. So we get log base 4 of, what goes in the numerator? 6. So we read top to bottom. We also read left to right in books. So same here. Left to right. 6 over 9. Now I'm going to put parentheses. Your book doesn't do parentheses, but I like that just because there's so many numbers in the same general area. But a question. What do we do with this 2? Haley? Ah, right? When we go to single logs, the 2 goes in the exponent. So this 2 here would be moved up to the exponent. So it goes squared. We move the 2 up to the exponent. But I do see that this can be simplified, because I noticed 6/9 isn't a simplified fraction. 6/9. Caitlin, what number can we divide both 6 and 9 by to make it smaller? 3. So Caitlin, what would, excuse me, what would 6 divided by 3 be and 9 divided by 3? 6 divided by 3? 2. Okay, and 9 divided by 3? 3. And then don't forget we had a squared, which actually makes me think I can do one more thing. Since these are both numbers, I can't actually square both of them. But the square belongs to both the 2 and the 3. One sec. What is 2 squared? 4. And what is 3 squared? Not 6. 9. So log base 4 of 4/9. That is our single logarithm. Adam, you have a question?
So where does 2 go?
This big 2 right here, it became the exponent 2 right here.
Oh, okay.
Okay? So in Single logs, it's the exponent. In expanded, it's pulled in front, multiplied. Yeah? Yeah. Yeah. Yes, Noah?
Why did we do it one way for the first example 3 and a different one for example 4?
Well, there were different problems. This was an addition problem, which meant we had to times. This is a subtraction problem, which meant we had to divide. Yes?
So why did we move from 6/9 to 2/3 and then 4/9?
Because we're simplifying. 6/9 is an unsimplified fraction, right? 6 and 9 are both divisible by 3. So we divided by 3 to get 2/3. And then you actually have to keep going until everything is simplified as compacted as it can go, which 2/3 can be squared. Okay, let's try another one. We're going to go the other way. The more we practice, the more you'll feel more comfortable. We're going to go the other way though, different directions. I think this will be our last one. We're going to example, what am I on? 5? Expand the logarithm. Okay, I'm going to make this problem as similar to the hardest one on the homework as possible. So this one is very similar to the very last problem on your homework. Okay, it's probably the most complicated one you'll see on the homework. Log base 7 of 7 square root, what? 4a to the third. Square root, I know, that's why we need to do one of these. Log base 7 of 7 square root, 4a to the third. Okay, we're going to expand. So, what operation is present here that we need to expand? Because we're trying to get it to either look like this in red, blue, or blue using the power, the quotient, or the product, the quotient, or the power rule. So we have to figure out what operation is there so we can expand it. The product rule, what's being multiplied?
7.
7 times the square root. Do you agree? Okay, so when we multiply, we have to do what? Add. Multiply, add. Multiply, add. All right. So we're going to split these up, keeping the same base. It has to always be the same base. Log base 7 of 7. We're splitting them up. Now we put plus, good. Log base 7, you have to keep the base, of square root 4a cubed. Now I actually claim square root is an exponent. Does anyone remember what exponent we get? You want me to sing another song? Not really. I don't have a song for this one, so you're in luck. Square root is an exponent, guys. I don't have a song for this one. I think that would be scary if I tried to freestyle. Ms. Bergstrom, can you help him out? What's the exponent for a square root? Does that sound familiar, guys? Square root is the 1/2 exponent. Cube root is the 1/3 exponent. Fourth root is the 1/4 exponent. So this is actually an exponent. Okay, I'm just going to rewrite and change it to the exponent. Log base 7 of 4a cubed raised to the 1/2, because all of that was underneath the square root, so it's all raised to the 1/2. Okay, guys, I actually see another multiplication. Don't you see it right here? 4 times a. So even though it looks like it's grouped with parentheses, it's being tricky. There's actually multiplication, which means when we multiply these, we actually have to add, multiply, add, expand them out to add. So this is going to be log base 7 of 7 still, plus log base 7 of, the first thing being multiplied is the 4. But don't forget the 4 has an exponent. What's the exponent for the 4? 1 half, because it's in the parentheses.
Oh, yeah.
Okay, plus log base 7 of a cubed
There you go.
to the 1 half. Whoa.
Oh, it's right.
Okay. I'll be right back down to that if you're writing it down. If we have, in a single log, if we have exponents, where do they go when we expand them? In front. We pull them in front. This is very similar to your hardest one on your homework, okay? The more you practice, though, it will get better.
So it'll be log.
Actually, you know what? This one can simplify. What 4 to the 1 half means square root of 4? What's the square root of 4? 2. So we can change that one to log base 7 of 2. We don't even have to pull out in front. Log base 7 of 7. But since this one has an a, not a number, we actually do have to pull out in front. But if you look here,
1.5.
times them and pull them out front, which would be 3 halves. Log base 7 of a. This is expanded, so I'm promising you there's one on your homework that's very similar to that. Okay, I made an error on this last example, so I'm re-recording because I got sidetracked. I forgot to explain that right here, where it says log base 7 of 7, when the base matches this number right here, it actually cancels it out. So this 7 really has an exponent of 1. So log base 7 of 7, the 7 cancel out the log, so all that's left is 1. Plus log 7 of 2 plus 3 halves log base 7 of 8. So that would be the official answer. I'm sorry about that. So example 6, let's just practice one of those really quick. If we have, say, log base 8 of 8 cubed, since the base and this 8 are the same, it cancels out the log, and the answer is the exponent, so it would simplify to 3. So just be aware of that. Okay, and the homework for this assignment is page 334, numbers 5 through 10, and page 342, numbers 1 through 4. I believe that comes out to be 10 problems, and if you do your assignment on time and in full and turn it in on time, you get 5 extra credit points, and you'll be in the running for a key card. 5 assignments on time, completely done with legitimate work, you earn a key card.